Hello everybody and welcome to P2's homeroom. Today we're going to take a look at the 4 universal forces, and those forces include electromagnetic, strong nuclear, weak nuclear, and gravitational forces. So, on to what each of these look like. Trying a new system out today, so hopefully things will go well. So first up is the electromagnetic forces, which is split into the electric force and the magnetic force. I still have my eraser on. Let's change that to a pen. Alright, so both electromagnetic forces, talking about electric and magnetic forces, deal with attraction and repulsion. So let's see, they can both attract and repel. Okay, so taking a look at electric forces, this is more on the atomic level where we are looking at atoms. As I'm sure many of you are aware, opposites attract. So if we have a negative electron and a positive proton, our negative is going to be attracted to the positive proton. But if I have 2 positive protons, they are going to push each other away. And the same thing would be if I have 2 electrons. They are also going to push each other away. So this is a really fun experiment that you can try at home. So if you have a balloon, or if you have a very, very fine tooth comb at home, you can take either one of these and rub them really just a lot all over your hair. So someone like me who has like a bunch of hair, this is a really, really good experiment. Someone who may not have a bunch of hair, you might have to try a little bit harder. So you can try either one of these, just rub it against your hair and then find a sink or a faucet. So where let's see if we can change our color. Hey, that's a pretty color. Where you can have water in a stream coming down. Going back to our green, actually, I have a better idea. Oh, the wonders of computer magic. Alright, so once you have taken either a balloon or a comb and run it through your hair repeatedly, put it next to a small stream. Don't make it a thick stream because then you're not going to be able to see. So just a nice, small, thin stream. And when you apply, that's supposed to be a balloon. So when you apply either one of these and push it next towards the stream, you should see the stream start to bend out of the way. And it's a really, really nice experiment that you can see at home. Another one that you can test at home is with magnets. And as I'm sure most of you are aware, magnets are going to have a north and a south pole. Generally speaking, your north pole is going to be all positive base and your south pole is going to be all negative base. And if you were like me as a child and you had 2 magnets that you tried to put next to each other, the south pole is going to be attracted to the north pole and vice versa, because we know that our negatives are attracted to the positive ends. But if you're also like me, and this was way more fun, if you took the south end and put it next to a south end, or north end and put it next to a north end, jump my little pluses and minuses, then they would actually push each other away because our negatives repel from one another. So these are our electric and our magnetic forces, where opposites, our negative and our positives, are attracted to each other, but our likes, positive and positive or negative and negative, repel each other away. And that is for electromagnetic forces. So we're going to hop over to nuclear forces. And this is something that we don't get to see very much because this is more at an atomic level. Let's actually click on the layer that I want to write on. There we go. Alright. So here we have a couple of rings around our nucleus. Draw a bunch of protons and neutrons. Protons, recall, all have a wonderful, lovely, positive charge, and our neutrons have negative charges. I'm sorry, our neutrons have neutral charges, so protons are positive, neutrons are neutral, and then on the outside we have our electrons, which have a negative charge. There we go. Much better. 3, 4. Okay. So previously we talked about how opposites attract, but like repels each other. And we can see the like repels each other with the electrons not being allowed to be right next to each other, but we see protons right next to each other. And that contradicts what we previously talked about. And so our nuclear forces are split into strong and weak forces. So looking at the strong nuclear force first, the strong nuclear force is what is keeping the protons and the neutrons in the nucleus. It only acts on a range of approximately 10 to the negative 15 meters. Now, if you'll recall, if you have a number and it has a negative, you take the decimal and you move it to the left. 3, 4, 5, 6, 7, 8, 9, 11, 12, 13, 14, 15. So you would move it to the left 15 times. So I have 15 zeros in front of my 1. That makes it a really, really tiny number, which is why it only works on the proton to neutron scale, because they're right next to each other, and that's about how far apart they are. So the strong nuclear force is what is holding our protons pretty much right next to each other. It's not an attractive force, but it is what is keeping them there, even with a couple of neutrons maybe buffering around the side. And so it is approximately, there is 100 times stronger than attraction. So this right here. This right here is why my protons can be really close to each other versus having my electrons being further apart. So the strong nuclear force works at a really, really tiny range and is 100 times stronger than our attractive forces. Here it is. Alright, so looking at the weak force, or the weak nuclear force, there's a couple things we need to clear up first. And so that is when we are looking at either a proton or a neutron. So this is a zero charge. It's a neutron. All of these particles have something called quarks. And quarks are these little subnucleic particles that have a positive or a negative charge in our atom, or in our subatomic particle. And it is technically possible for a nucleus to turn, for a neutron to turn into a proton. So say, for example, we have 137, 55 cesium, if you look on your periodic table. So this means I have 55 protons, and the remainder of the mass is what adds up to make 137 either protons or neutrons in the nucleus. Like I said, it is possible for one to turn into the other. The way that happens is something called beta emission. You'll learn more about this in chemistry, but just kind of a nice heads up is, so say one of these little negative quarks right here, it pops off, just completely detaches. So it produces an electron. Well, because I'm getting rid of a negative, I'm left with more positive. I have 2 positive and 1 negative, so this right here is left with a positive. Well, if I gain a positive, that means I gain a proton. And so I jump from 55 to 56, but the number in the nucleus still stays the same, and that puts it at barium. And so this right here is a really good example of a weak nuclear force, and that weak nuclear force is what is keeping these quarks. I'll write it out for you guys. And so it's keeping these quarks together. But like I said, occasionally one of these comes off during radiation. And again, that's something that you'll learn more about in chemistry. I can't go up, can I? One moment. There we go. You can actually see. All right. And last but not least on here are the gravitational forces. And this is the one that we are the most familiar with. This is, as we have heard, is what caused the apple to fall on Sir Isaac Newton's head. Whether that actually happened or not is up for debate, but it still brings the point of gravity is what is keeping us here on the Earth versus us flying off into space. But what you may not know is that gravitational forces is attraction between two masses. And yes, that is completely accurate. So I have body mass and my husband has body mass. So technically there is attraction between us. Which, I mean, we already knew that. But anyways, like, I could take two pencils and they both have mass. And so technically there is attraction between them. The difference is the scale of everything. So a couple of things that are on maybe a moderate scale, we'll say that they're about the same size, pretend those are the same size, are going to exert the same amount of attraction on each other. So we're going to pretend that those arrows and those circles are the exact same size. We don't notice this very much because we are on Earth. And from our perspective, we're going to pretend that that's a nice circle. The Earth is a really, really large, massive object. So it is going to exert a really large force on an object of slightly smaller value. Versus if you have two smaller objects, then they're only going to exert a little bit of force. And so we don't really get to see this happening a lot, but one of the best examples that we get to see is where we have the Earth, and then we have the Moon. And so both the Earth and the Moon are exerting force on each other. The Earth is what is keeping the Moon in rotation around it, as well as several different satellites that pass by, or TIE fighters, that too. But the Moon, we don't really get to see the attraction of the Moon on the Earth too terribly much. One of the best ways for us to determine this is with high tide and low tide. So for things that have high tide, that means the Moon is just a little bit closer to the Earth at the time, versus low tide, the Moon is a little bit further away. And so the distance between objects as well as their mass affect each other for gravitational forces. And so those are the 4 universal forces. Hope you guys enjoyed this. It was a nice, fun thing to do. Thank you guys for just being awesome through all of this. I hope you all are doing well. I really miss you guys. And y'all just take care. Love you all. Bye.